everyone. In this recording, we'll be going over complex numbers. Our goal is that by the end of this presentation, you'll be able to use the imaginary unit I to write square roots of negative numbers. You'll be able to add, subtract, multiply, and divide complex numbers. You'll be able to use complex conjugates to simplify quotients. You'll be able to solve quadratic equations with complex solutions. So the imaginary unit I can be defined as I is equal to the square root of negative 1. And we need this definition because sometimes quadratic equations have no real solutions, one of those being the function x squared plus 1. So we're given an example, the square root of negative 9. So that is the same thing as writing the square root of 9 times the square root of negative 1. So we stated the square root of negative 1 is equal to I, and the square root of 9 will be equal to 3, so we're left with 3 times I. If we're given negative 5 plus the square root of 9, that is the same thing as saying negative 5 plus 3i. So a complex number is written in standard form, a plus bi. So a is the real part and bi is the imaginary part. If b is equal to 0, then that means that the number a plus bi is real. And if b is not equal to 0, that means that the number a plus bi is imaginary. So a number of the form bi, with b not equal to 0, is a pure imaginary number because it has no real part. So now for our number system relationship. All real numbers are part of the complex numbers because every real number can be written as a plus 0i. Then we have pure imaginary numbers, so the numbers without a real part, and those are also part of the complex numbers. So those numbers are of the form b times I, where b is not equal to 0. So now two complex numbers, a plus bi and c plus di, are equal if and only if a plus bi is equal to c plus di, and that happens only if a is equal to c, so their real parts are equal, and b is equal to d, their imaginary parts are equal. So now we have some quick examples. 4 plus 0i is a real number because it has no imaginary part. 0 plus 5i is a pure imaginary number because it has no real part. If 3 plus 2i is equal to c plus di, then c is equal to 3 and d is equal to 2. So if we're given z is equal to a plus bi, then the complex conjugate will be a minus bi. So we just switch the sign between the a and the bi. So, for example, we have 1 plus I. Then the conjugate is 1 minus I. So when we multiply a complex number by its conjugate, we will get a real number. So 1 plus I times 1 minus I is equal to 1 squared minus I squared. So I squared was negative 1, so 1 minus negative 1 is equal to positive 2. Now for 4 minus 3i, the conjugate is 4 plus 3i. So if we multiply 4 minus 3i times its conjugate, 4 plus 3i, we get 4 squared minus 3i squared. And upon simplification, we get 25. So in order to write a plus bi divided by c plus di in standard form, we multiply both the numerator and the denominator by the conjugate of the denominator. So the conjugate of c plus di is c minus di. So we would multiply a plus bi times c minus di and c plus di times c minus di. So here we have an example, 2 plus 3i divided by 4 minus 2i. So we'll multiply by the conjugate of 4 minus 2i on both the numerator and the denominator. So the conjugate of 4 minus 2i is 4 plus 2i. So we'll have 2 plus 3i times 4 plus 2i and 4 minus 2i times 4 plus 2i. So in the numerator, after multiplying all the terms, we will get 2 plus 16i, and in the denominator, we will get a real number because we're multiplying by the conjugate. And in our case, that is equal to 20. So we'll get 2 plus 16i divided by 20. In the simplified form, or the form in standard form, will be 1 divided by 10 plus 4 over 5i. So before carrying out any operations, we need to convert complex numbers into the standard form. So we define our principal square root. So when a is a positive real number, then the square root of negative a is equal to the square root of a times I. So another important thing to remember is that the rule, the square root of a times b is equal to the square root of a times the square root of b, is not valid when both a and b are negative. And we see this in our first example, 1a. So we have the square root of negative 3 times the square root of negative 12. So first we convert them into standard form. So square root of negative 3 is equal to the square root of 3 times I, and the square root of negative 12 is equal to the square root of 12 times I. So the square root of 3 times the square root of 12 is equal to the square root of 36, which is equal to 6. Now I times I gives us I squared. And I is equal to the square root of negative 1, so once we square that, we get negative 1. So 6 times negative 1 is equal to negative 6. Now part B, we follow the same process, but now we are subtracting. And for part C, we have two terms. Now for example 2, we are told to solve the quadratic equation 3x squared minus 2x plus 5. So we recall that our quadratic formula is given by x is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So after we plug in all our terms, our a, b, and c, we're left with 2 plus or minus the square root of negative 56 divided by 6. Now the square root of negative 56 is equal to the square root of 56 times I. And 56 is divisible by 4, so we can rewrite that as the square root of 4 times the square root of 14. So the square root of 4 is equal to 2. So now we're left with 2 plus or minus 2 times the square root of 14 times I divided by 6. Now we can simplify and factor out a 2, and we're left with 1 plus or minus the square root of 14i divided by 3. So now for a plus bi times c plus di, we will distribute each of the terms, and then we will combine like terms and write the result in standard form, a plus bi. So we have a times c plus a times di plus bi times c plus bi times di. So then rewriting with the real portion, we'll have ac minus bd. And for the imaginary portion, we'll have AD plus BC times I. And we know that I squared is equal to negative 1, which is why we have the negative BD. Now a quick note is that the product of a complex number and its conjugate is real. So now we have some examples that you can practice on your own, and the answer is given so that you can check your work. So lastly, if we're given a sum a plus bi plus c plus di, we need to add our real parts, so a plus c, and we add our imaginary parts, b plus d times I. Now the same rule applies to the difference, a plus bi minus c plus di. So we'll do a minus c, the real part, and b minus d, the imaginary part. So the additive identity in the complex number system is 0, and the additive inverse of a plus bi is negative a minus bi. So here are some more worked examples so that you can practice on your own, and the answer is provided so that you can check your work.